Assalamualaikum warahmatullahi wabarakatuh. Thank you for this opportunity to participate in the National Conference of Technology on Community and Environmental Development 2024. Before I start to present, I would like to introduce myself. My name is Thoharudin, come from Department of Mechanical Engineering, Universitas Muhammadiyah Yogyakarta, and there are my team, Sudarja, Sunardi, Fitra Anugrah Kusuma Yuda, Arif Setia Nugroho, and Akhil Pujianto. I would like to present a paper with the title of Design and Simulation of Double-Nozzle Venturi Bubble Generator for Aeration System. Aquatic organisms rely on the oxygen for breathing. Without any sufficient oxygen, the organic organism in the water will die because oxygen is very essential for our life. One of the technology to prevent the oxygen content in the water is aerator. So the aerator is commonly used to enhance the DO concentration by facilitating the aeration system. One of the kind of the aerator is Venturi bubble generator. Is one of the technology that use Bernoulli principle to suck the oxygen into the water body by using this equation. It is the Bernoulli equation. It is the flow energy, kinetic energy, and potential energy here become a constant. So the picture of the commonly used Venturi bubble generator can be observed here. The left-hand side is the water inlet, and the right-hand side is the mixture between the water and the air outlet. So the Bernoulli principle shows that here the water inlet here, the pressure is very high, so the velocity in here, water in here is low. And because of the different area between the water inlet and the throat area, the velocity in the throat area become larger on so the speed is increased, so the pressure will decrease significantly. So because of the decrement of the pressure, the air can be sucked into the throat area. So in the divergent section here, so the mixture between air and water can occur. So the bubble can form in that area. In today, many computational dynamic work can be used to simulate many cases, including the Venturi bubble generator flow. So we try to study Venturi bubble generator with the type of the double nozzle and simulate it in using CFD to take a picture of the behavior of the flow, including the bubble formation and the flow and so on. And then there are many devices that are actually available in the industrial process. It is the Venturi bubble generator with 1 inch, and it is the half inch. And then we propose a new double nozzle Venturi bubble generator with special design. For example, it is the shorter than the actual design of the half-inch Venturi bubble generator. And then for the typical Venturi bubble generator only have 1 nozzle in the throat, and we propose 2 nozzle, first in the throat and then the second in the exit of the Venturi bubble generator. And then the size of the proposed Venturi bubble generator is not so very close to the 1 inch in the diameter. And then for the length is shorter than half inch of Venturi bubble generator. So we can convert it into simulation domain like this one. That is the 3-dimensional domain of the computation for simulation. And because we want to investigate the behavior of the bubble, not only in the Venturi bubble generator, but also in the water body. So we add additional computational domain like this one. It is body water with the length of the 20 centimeters. Then for the simulation, we use ANSYS as the software for simulation of the Venturi bubble generator. And then the mesh shape we construct using tetrahedron in the simple way to get a mesh. And then the cell number we can calculate it. We can calculate the number. The first for the half inch, it exhibit 64 point something, 64,000 point something. And then for the one is Venturi bubble generator is 64 point something. And then for the double nozzle Venturi bubble generator is 69,000, 69,000. And then for the simulation model, we use symmetric transient simulation because for the symmetric transient simulation, we can only create that computational domain is only a half. Yeah. And then the turbulent model, we use K omega SST turbulent model, which this turbulent model typically used for the flow with the spiration. Like in the multi-phase process, typically I use K omega SST turbulence model. And then for the multi-phase method, we use Eulerian to fluid model with population balance model. So we can predict the diameter and distribution of the bubble formed in the Venturi bubble generator. And then the drag model, we use Seiler-Naumann, the bubble dispersion process. We use Lehrer model, and then for the bubble aggregation, we use the equation of Luo model. And then the water flow rate, we get it in constant in 30 liter per minute. And then for rate of the air in 2.58 liter per minute as we observed in the double nozzle Venturi bubble generator in the experiment. And then it is the result for the simulation for the pressure distribution. We can observe that at the convergent area, the pressure is very high, especially can be observed at the half inch and double nozzle inch. And then after that, the pressure gradually increase from the neck to the water body. And then for the 1 inch Venturi bubble generator, the pressure difference is not significant. And then we can observe on the right-hand side here, it is the pressure drop and head loss due to the flow occurred during in the half inch, 1 inch, and double nozzle Venturi bubble generator. We can observe that the pressure drop occur on the half inch and double nozzle Venturi bubble generator has very close. And however, for the 1 inch Venturi bubble generator, the pressure drop is not so high, so the head loss is also very small head loss. A particular observation we can observe this one for the double nozzle Venturi bubble generator. We have a very large deviation here for the specifically for the pressure drop here. It indicates that the flow in the double nozzle Venturi bubble generator is not so good. So the fluctuation of the flow occur. So the pressure of the pressure drop occur and the flow is also happen in large fluctuation. And it is the velocity distribution here. We can observe that for the half inch and double nozzle Venturi bubble generator, the velocity after the next section is very high. It's typically different from the one is here. So the velocity between the divergent section and the convergent section and the neck or throat section is not so have a large difference. And then it is the kinetic turbulence here, and then it is turbulent intensity here. And then we can observe that the most turbulent can be observed by the double nozzle Venturi bubble generator. So it indicates that the mixing between the water and air happen very large in double nozzle Venturi bubble generator. And then after that, we can observe the bubble distribution both in the Venturi bubble generator in the water body here. And then we can observe that the bubble generated from 5 micrometer until 5 millimeter here. And then we can observe that half-inch Venturi bubble generator can produce a very low diameter of the bubble. So, however, because the velocity of the exiting the Venturi bubble generator is not so good, so there is any agglomeration of the bubble. So from the teeny bubble size, so it can grow to large bubble size. And different from half-inch Venturi bubble generator, 1-inch Venturi bubble generator has a separation section here. So the water flow in the bottom of the Venturi bubble generator, and then the air flow at the upper side of the Venturi bubble generator here. So it is a special, maybe it is a special issue that can be investigated furthermore regarding one is Venturi bubble generator. So even though the flow is not so fast, but the bubble generated has very low that comparable with half-inch Venturi bubble generator. And then it is the bubble size distribution here. We can observe that the double nozzle Venturi bubble generator has very narrow of the bubble size distribution from 0.005 millimeter or 5 micrometer into 2.2 millimeter. It is not comparable with the other Venturi bubble generator that distribute until 3.4 millimeter for 1-inch Venturi bubble generator and until 5 millimeter for 1-inch bubble generator. However, our proposed double nozzle Venturi bubble generator has a fluctuation in the flow, so the specific energy loss is very high. So even though the average value is below the half-inch Venturi bubble generator, but the deviation is very high from below to the higher value of the half Venturi bubble generator. So by this study, we can conclude that the half-inch Venturi bubble generator exhibits significant pressure discrepancy between its inlet and slide section, leading to notable energy loss. The 1-inch model shown the more consistent pressure distribution, resulting in minimal energy dissipation. And then the proposed double nozzle Venturi bubble generator show almost comparable pressure drop and energy loss with the half-inch Venturi bubble generator. However, it demonstrates many advantages, including the first, a higher exit velocity contributing to wider bubble distribution in the water body. Higher turbulent intensity, promoting the bubble breakup into smaller size and avoiding the bubble agglomeration. The average bubble size exiting from the Venturi bubble generator, produced by half-inch, 1-inch, and double nozzle, were 204, 216, and 109 micrometer. And the last double nozzle Venturi bubble generator provide the narrowest bubble distribution ranging from 5 micrometer to 2.2 millimeter. And it is the installation of Venturi bubble generator that connected to the solar energy system. You can observe it, and then it's installed in the lake, and you can observe the bubble generated by the Venturi bubble generator here. So we can see the fish is very exciting because of the addition of the oxygen due to installation of the Venturi bubble generator. Thank you for your attention. Assalamualaikum warahmatullahi wabarakatuh.